this zero cement concrete by using a normal sand. But the shrinkage is larger than that, 400, 500 sometimes. But it is suitable for the precast technologies. And this is right-hand side is shrinkage. Green line is zero cement concrete. After the casting, the shrinkage is the plus side. This is we use as I said yesterday, we use expanded additive as an alkali activator. So this is why this is 200 micro go to the plus side. Then after that, the dry shrinkage goes down to the less than the 200. This expanded additive is a very special material, but usually we use the normal concrete, and this material is calcium based. And now we are doing joint research with Sheffield University, but in Europe it is not impossible to procure this expanded additive. So we just doing to look for another alkali activator to realize this zero cement concrete. In 2019, we just built the zero cement concrete plus aramid fiber non-metallic girder in our concrete one of the in our concrete factories. Span length is very small, 12 meters, but I think this is a future, one of the future solutions to reduce the CO2 as precasters. Okay, curing, steam curing is very important. Low carbon concrete, the strength increasing very slow compared with Portland cement concrete. And of course, as a precasters, we have to increase the speed of the concrete strength. And this is very beginnings of trial in one of our concrete factories. And to reduce CO2 from the boiler, we use the hydrogen boiler like this, but this is very expensive. So we this is a trial, but this is not our final solutions. But this is very important to show this kind of the low carbon activities to our investors. So we have a hydrogen boiler, and the capacity of this boiler is very small, 250 kilos per hour, and the amount of hydrogen used is only the 60 normal cubic meter per hour. So this is only the few percent to reduce CO2, but in the future, the hydrogen price is very low, and it is one possibility to reduce the CO2 by the by the steam curing of the low carbon concrete. And another way is like this. This is just the laboratory's test level. And everybody knows it's a kind of carbon capture technologies. And before doing this, we have to separate CO2 from the boiler exhaust gas and pass through it and the alkaline solution to convert it into the calcium carbonate. And you can see the white powder. This is we can use the CO3 as additive of the concrete. So this is trial, and we just started to develop the special membrane to separate the CO2 from the exhausted gas with some chemical companies. But it's just the beginning. But also, this is one of the solutions for the precasters. I don't know in Brazil you use steam curing a lot, but as far as you use low carbon concrete, you have to solve this steam curing CO2 emission to reduce it. Okay, so I will talk about the next cycle of the precast structures. We have to think about multi-cycle use of the precast members, as I said yesterday, and easy to demolish, and also to assess the member, used member, and make it as a new members. In the red C and D stage. And this is example of the prefabricated off-site construction in the world. This is an example in Australia. And the room the structure is steel. They just prefabricated the whole of the room in the factories. They transport it at the site and just put on the stories. And in this case, in Melbourne, Sydney, this building is very, very high-rise building because the Australia don't have any earthquakes. They can do that. And this is also the very, very famous in Singapore. The room is covered by the concrete. In this case, it's the same to just put on each floors and completely prefabricated. But in Japan, we cannot do that because Japan is earthquakes-prone countries, and we need some structures, very, very stiff structures. And we have to separate the structures and the room. And this is the definition of the manufacturing. In order to do the manufacturing, and the separation of the structure and the room is needed. So I just, this is the reference of the bottom side is the website. At least its original performance is warranty. Warranty is very important. That is equivalent or better than the original one. This is very important things. But nobody knows how to do it, how to warranty the used members make the new members. So remanufacturing is a very, very new way of thinking, but in order to reduce the CO2 in a product stage of the precast structures, remanufacturing is another solution to do that. So please think about that. And also, of course, we are just studied to how to warrant it is new members. Okay, so this is the difference between the reuse. Reuse go to the user, but the members is deteriorated. They're not new members. And the recycle go to the material stage, and everything is completely changed, as the Professor Gitu said this morning. But remanufacturing, the member go to the components fabrication to assess how to deteriorate and to warrant this is a new members. So this is a very, very new concept and also the new technologies. But we need to develop many, many things. So this is the same idea which I showed yesterday. And the structures connected by unbonded tendons to make it easy to demolish. And also loom is another prefabrication, but it's not structural members. Just put into the frame, and also otherwise after the renewal of the room, you can withdraw these members from the structure and so put into the new members. This is the basic concept. In the horizontal axis and the vertical axis, every member is connected by unbonded tendons. But in Japan, this new concept is not allowed at this moment. So we are doing the joint research with the university, Kyoto University, and then we just, after that, we just apply to get some certificate by the authority to use these new technologies. Okay, this is a concept. And we already have the frame precast concrete technologies, and also already have the prefabricated rooms like this. But combined to technologies, reinforced concrete structure, it's okay. We just built the same as before and just put the new rooms, it's okay. But in order to make it remanufacture, the structure should be the process concrete structures. So, but before that, we made a mock-up trial in our R&D center. But this is reinforced concrete structures. And this new technique is we should confirm many things, the precisely and the transportation from the more than 300 kilometers. During transportation by trailer, they have torsion. And also after the arriving in the site, the room has some residual torsion deformation. It is impossible to make the precisely. So the trailer is very special, developed by the fabricators of the room, and we checked everything here. This is a process, and this is already well done by us, the reinforced concrete precast technologies. And setting of the room, after that we set the beam. This technology is also done many times. And in this case, the slab is also the half precast members. Some parts are just in situ concrete, but we can do this to the whole precast members. And walls, we don't have walls. And of course, basically we don't need precast floors, but the room is non-structural members. We just put small bearings to set the room. And wall, we don't need it between the two rooms, but the distance of room is about 20-30 centimeters, just here. And also this is very good for the reduced acoustic noise from the adjacent rooms. We confirm it already. Okay, so we are going to build a new R&D center by using this precast and tension process concrete technologies. We just finished get the certification from the authority. We just wait to start the construction. And by using precast and unbonded tendons, we don't have any data. We have to check everything. That this is the test of the column. This is the test of the beam. And the beam and column connection is very important to assure the performance. Sometimes we allow to some cracks and some failure, but sometimes we don't allow to any damage during earthquakes. So this is the performance. And sometimes we use we will do in the future. We will do this kind of test and get the hysteresis curve. And also finally we get the design criteria like this. So we need a time, a little bit time to confirm everything by using these new technologies. Okay, so during service of the precast and unbonded tendon, especially my country has earthquakes, we have to check, we have to monitor the structures, and sometimes in order to avoid any damage during earthquake, we have to combine with base isolation and the damping of the structures. I'll show you a little bit. And we have already very sophisticated system. Of course, we use an accelerometer and already put the bridges and very old building almost collapsed to check how small difference we can detect by using these technologies. So we can get the small change of the structures and increasing of the road and sometimes the middle class of earthquakes. This works very well. And we confirmed up to failure by using a moving shake table test in Kyoto. It works well too. We've confirmed already. And also this point, the big difference between before the earthquake, after the earthquake, we detect this point and we announce the owner this building can be used after earthquakes, or you need a more detailed inspection. This kind of information we needed to be the business continuity program. And dumping system. This is a very new dumping system. We call it a seesaw dumping system. And the mechanism is very, very simple. This is the damper, and this is a seesaw. We have rod to transfer the horizontal displacement to the vertical displacement. So this is the Chebyshev linkage, which is I didn't know that before this R&D, but this is very famous mechanism because this endpoint is never moved vertically, which here. So this system can be used by using a Chebyshev system. Oh, you can see that. So, sorry. This is animation, okay, this. So the point P never moved to the horizontally, vertically. And we checked this behavior in laboratory test. It's about almost full size, and by using this is a special damper, and also this is the viscous damper. After that, we can reduce by using these type of dampers, reduce the displacement up to the 1/5. So this is very easy to install the existing buildings and compare with the conventional way, like damping brace, and also a little bit damping brace, and this new damping system is compared with the conventional one. We can reduce the cost of this damping system. So if the case in the precast and unbonded tendon, and also is the case the concern about the vibration or the resistance during earthquake, we need this kind of damping device to realize the remanufacturing this new kind of technologies. Okay, conclusions. To respond to carbon neutrality and develop new market as precasters, transition until cement and reinforcing steel achieve zero carbon. This is important. And also ensure the durability of low carbon concrete with low pH. This is another key things. And creating a system to allow for the expansion of the buildings and the reduction of the buildings, and adding the member and reducing the member by release the processing tendons. And this is the very, very important for the precast industries. And the monitoring and assessment of technologies is to concrete, and the design criteria is another key things for the warranty of the manufacturing. The warranty is very important. And the reduction of CO2 emission by steam curing when using low carbon concrete is another key. And then finally, of course, you should use renewable energy in your factories. Okay, so Roman concrete, there are no steel reinforcement, and the concrete itself is very, very high durable, more than 2,000 years. It's a proof. But this is not Portland cement. It's a geopolymer cement, relatively saying. And also the new technologies, by using new materials, low carbon, zero cement, concrete, plus plastic fiber. I don't know, it is the same durability. They have the same durability, but it is one of the way to go to the carbon neutrality, to realize the carbon neutrality as a precast industries. Okay, another things, lastly, and water and sand. Water, the Professor Getsu mentioned about a little bit. And in Japan, we use tip water in the mixing of the concrete. So you can imagine in the world, about 2 billion people cannot reach to the drinkable water. And if we use the plastic fiber and the reinforcement of concrete, we can mix by using seawater. And unfortunately, our factory is far from the sea, but if the chance to build new factories, we have to locate it near the sea to use seawater in the mixing. And also sand. The concrete uses many amount of sand, huge amount of sand. It is almost 205 meter wall on the equators. So I cannot imagine that this amount of sand. But some researchers in his FIB members started to research to use a dune desert sand as a concrete, because now we have very sophisticated plasticizer, and also they reach to the more than 100 MPa by using a desert sand. This is another way, not related to the CO2, but strongly related to the SDGs. Thank you for your attention.
Eu vou pedir para que o Akio permaneça aqui no palco. E gostaria também de chamar o nosso próximo palestrante, que é o professor Fernando Stuck, que vai falar sobre resistência ao fogo. Mas gostaria de chamar também uma pessoa bastante importante, que foi selecionada por critérios da FIB, por critérios nossos aqui também no Brasil, mas que é uma prerrogativa da próxima vice-presidência, ter como chair do grupo jovem da FIB, o jovem, conceito de jovem, é que se tudo acontecer como deve acontecer, e ontem o Akio comentou isso, eu assumo ano que vem a vice-presidência da FIB 23, 24, e depois 25, 26 a presidência. E a FIB estabeleceu que, junto com a vice-presidência e o presidente, um jovem engenheiro do mesmo país, que tenha atuação preferencialmente junto à academia, mas também junto à indústria ou a um escritório de projeto, estivesse comigo fazendo o mesmo papel na liderança jovem. Então, eu gostaria de chamar o Marcelo Mello, que é do escritório Casa Grande, de projeto estrutural do Rio de Janeiro, que vai ser o nosso braço jovem junto à FIB, aproveitando a presença do professor Stuck, que é o head da delegação brasileira, o Akio, o atual presidente da FIB, e eu gostaria só de convidar o Marcelo para a gente fazer uma foto juntos aqui, e 2 minutinhos para você falar alguma coisa. Vem cá. Vamos ver aqui.
Bom dia, gente. Tudo bem? Eu não estava esperando isso. A Iria não comentou nada que ia me chamar, então estou um pouco nervoso. Mas eu estou muito feliz de ter sido convidado e de estar participando disso. Espero conseguir representar a gente, os engenheiros jovens lá do Brasil, na FIB. Então, estou trabalhando muito nesse sentido e espero representar direito o Brasil lá. E, assim, sempre desenvolvendo novas tecnologias aí e avançando com o concreto brasileiro. Obrigado.
É assim que a gente começa. Eu também, a primeira vez que precisei falar, chegaram no local e disseram, a Iria vai dar uma palavra. E aí eu comecei a falar, nunca mais parei. Então, Marcelo, pode ficar tranquilo que é assim que começa mesmo. Professor Stuck, EGT Engenharia, Poli USP, acho que dispensa muitas considerações e apresentações, mas nos deu, juntamente com o Cassiano, que havia feito mestrado em estruturas pré-fabricadas de concreto em relação à resistência ao fogo. Vocês têm as informações todas na publicação, mas eu gostaria de agradecer por ele ter sido o revisor deste importante capítulo e ter atuado conosco, né, Carlos, nesse item específico, né, da revisão da 9062, porque nós tínhamos importantes interfaces, inclusive com a norma de resistência ao fogo. Stuck, the floor is yours.
Sim, senhora, as ordens. Eu não sei se vocês sabem disso, mas eu estou em casa, habituado a dizer que manda quem pode, obedece quem tem juízo, né? Aqui é exatamente isso que aconteceu. Ela tem uma capacidade bárbara, estratégica, administrativa, cara. Uma maravilha. Ela vai ajudar o Brasil a ir para frente. Podemos começar? Não, podemos. Bom, ela já apresentou, eu queria lembrar o Cassiano que ele fez a maior parte disso que está aí. Como é que faz para andar para frente? É o verdão grande. Isso. Bom, o foco e para voltar para trás é o vermelho, né? Deixa eu testar para ver se funúncia. A ideia é falar um pouco da 9062, com foco no incêndio, que foi o que de mais, embora outras coisas novas também houvesse, o que mais novo houve foi incêndio. E quando a gente fala de incêndio, precisamos pensar num monte de coisas. A primeira é reduzir risco de incêndio. Então, cuidado com o volume de material combustível, mas também é possível ventilar como? Depois, controlar o fogo logo que apareceu, logo de início. Super importante, limitar a área de fogo, né? Quer dizer, eu tenho que ter compartimento, tenho que compartimentar, ter corta-fogo, etc. Depois, criar a rota de fuga, para quem está lá dentro, né? E, ao mesmo tempo, a gente não chama também, mas é rota de entrada, porque o bombeiro precisa ir lá proteger, né? Agora, uma coisa que é o que a gente vai focar um pouco, é que eu vou calcular a estrutura, mas o cálculo da estrutura na condição de incêndio é bem diferente do cálculo usual, porque como o incêndio é uma coisa, é um evento raro, mais ou menos raro como um incêndio, como um terremoto, a gente não tem muito hábito de calcular terremoto, né? A gente vai querer que a estrutura não colapse, dá tempo para todo mundo fugir, e depois, se Deus quiser, não cai. Lembra de Andraus, por exemplo, que não tinha se calculado com incêndio, conseguiu todo mundo sair, o bichão ficou em pé ainda, deu para segurar. É isso que a gente quer. Mas é lógico que depois que acontece isso, você tem que reparar, e muitas vezes reforçar. Não dá para voltar a utilizar direto, né? Essa é uma visão importante que a gente deve ter. Quando houve o terremoto lá em Convenção, eu lembro de um pessoal lá no Chile que ficou bravo. Como a gente fez uma norma, não podia cair nenhum prédio. Não é assim que a gente